Hello. Today we will be demonstrating QPS's TPD sensor on an emulated transformer. The items used in this demo are the laptop, the TPD system, a fiber optics PD sensor, an emulated transformer, and a piezoelectric actuator. The TPD system contains two LEDs on the front panel, one for power and the other to indicate that the data acquisition system is ready. The PD sensor is made with fiber optics. The package contains two magnets that hold the sensor to the walls. It will stand orthogonally to the targeted surface. The signal generator is called Smart Power Sonic. It contains the power amplifier to drive the actuator. The switch allows a selection of various signal frequencies, ranging from 30 to 100 kHz at 10 kHz intervals. The black cylindrical item is the piezo actuator. It is driven by the signal generator and is designed to radiate acoustic waves in the oil. The red toolbox has metallic walls which contain motor oil. This setup emulates the interior of a transformer. The TPD system will be connected to the laptop via a USB cable, and the software used in the demo contains the user interface showing time domain and frequency domain signals. The PD sensor is mounted to the walls of the toolbox just as we would mount it to the walls of a transformer. The piezoelectric actuator is immersed in oil and creates bursts of acoustic emissions. These are the same signals that would occur during partial discharge in a transformer. Various frequencies simulate different PD processes, such as defects from cellulose paper or air bubbles in the oil. Now that all the components are hooked up, we can start the demo. We will now show the broadband performance of our PD sensor. We first set the signal to 30 kHz. Notice the captured PD signal contains an interference pattern of multiple reflections. The lower the frequency, the lower its propagation loss. What we are seeing here are multiple reflections of one signal. Now we set the frequency at 40 kHz. The reflection still shows multiple peaks, but the attenuation is clearer. Moving to 50 kHz, the number of peaks further decreases. At 60 and 70 kHz, the amplitude has slightly diminished. At 80 kHz, there are less reflected peaks. At 90 kHz, the signal response actually becomes stronger. It shows near saturation. At 100 kHz, it looks like there's still chance of reflection. We have learned from published literature, oil can support a signal range from 30 kHz to 300 kHz. This shows that our PD sensor is broadband in nature and would allow the customer to analyze the source of the PD signal.